Today, we're diving into one of the wildest, most powerful phenomena in the entire cosmos: gravitational lensing. It's this incredible idea that the universe itself can act like a giant telescope, showing us things we could never, ever see otherwise.
So let's start with a statement that probably sounds completely wrong, like it breaks a fundamental rule of physics. Here it is. Light doesn't always travel in a straight line. On the mind-boggling scales of the cosmos, that's just not the whole picture. The universe can bend light. And believe me, it does.
To get your head around this, just picture something simple. Imagine you're looking at a candle flame, but you're looking at it through the curved base of a wine glass. That glass totally warps and distorts the light, right? You see weird arcs and maybe even rings. Well, the universe does pretty much the same thing, but its lens isn't made of glass, it's made of gravity. So, what is this cosmic wine glass? It's gravity itself. And to really understand how this works, we have to go back to one of the greatest showdowns in the history of physics. In one corner, you have Isaac Newton, who saw gravity as a pretty straightforward force, one thing pulling on another. And in the other corner, you have Albert Einstein, who came along with this radical idea that gravity is actually the curvature of space-time itself. And they both made a very specific prediction: by how much should the sun's gravity bend the light from a faraway star? As you can see, their numbers were not the same. And it wasn't just a small difference. Einstein's prediction was exactly double Newton's. So during a solar eclipse back in 1919, astronomers set out to measure it. And guess what? Einstein was spot on. This one observation proved him right and basically made him a global superstar overnight. The physicist John Wheeler put it so perfectly. It's this beautiful two-way street. Matter tells space-time how to curve, and that curved space-time then tells everything else, including light, how it has to move. Light is just trying to take the shortest path, but in a curved universe, the shortest path isn't a straight line anymore.
Okay, so we've established that massive objects bend light. But what does that actually look like when we point our telescopes out into the universe? Well, it turns out this cosmic funhouse mirror has three main effects, all depending on the size of the lens and how everything lines up.
First up, the one that gets all the attention: strong lensing. This is the big one, the most spectacular version. It happens when you get an almost perfect alignment between us, a really massive object like a galaxy cluster, and some poor, unsuspecting light source way off in the distance behind it. Now, when this happens, you get these absolutely mind-bending images. You'll see what looks like 2, 3, or even 4 distinct objects that are actually just multiple images of the same object. Or the background galaxy can get stretched out into these enormous, brilliant arcs. And if the alignment is just right, you get a perfect circle of light called an Einstein ring. It's incredible. We didn't even see one for the first time until 1979, when scientists figured out the 2 quasars they were seeing were just an illusion, 2 images created by a single cosmic lens. Now, of course, a perfect alignment is pretty rare. Most of the time, things are a little bit off. And that's where weak lensing comes in. It's way more subtle. It doesn't create multiple images, it just ever so slightly distorts the apparent shapes of distant galaxies.
And I mean really subtle. You could stare at a single galaxy your whole life and never notice it. So how do we see it? Well, astronomers use a really clever statistical trick. They analyze the shapes of millions of galaxies in one patch of sky. Since galaxies should be oriented randomly, if you average them all out, any pattern that emerges, well, that's not random. That pattern is the cosmic shear, the faint collective stretching caused by the gravity of all the stuff in the foreground. And this is our #1 tool for mapping the invisible.
Okay, so we've gone from huge galaxy clusters down to, well, even smaller. What if the lens is just a single star? Or maybe even a planet? That's microlensing. The light gets bent, but the resulting images are so tiny we can't possibly see them as separate dots. So how do we even know what's happening? We'll look for changes in brightness. See, as the lensing star drifts in front of a more distant star, its gravity acts like a magnifying glass. For a few days or weeks, the background star appears to get brighter, then dimmer again, in a very specific bell-shaped curve. And here's the really cool part. If that lensing star has a planet orbiting it, the planet's own tiny gravity adds a sharp little spike to that smooth curve. It's an amazing way to find planets that are completely invisible to other methods, including rogue planets that wander through space all by themselves.
So, we've got all these beautiful, strange, distorted images of the cosmos. But are they just pretty pictures to hang on a wall? Or can we actually use them to do some serious science? The answer is a resounding yes. This is where it gets really important. To understand why, you just have to look at what the universe is made of. All the stuff we know and love. Stars, planets, gas, you, me. That's normal matter. And it only makes up a pathetic 5% of the universe. The vast majority is this stuff we call dark matter and dark energy, and it's completely invisible.
And this is what makes gravitational lensing a complete game changer. See, gravity doesn't care if matter is visible or not. It only cares about mass. Lensing is literally the only method we have that can directly see and map out the location of that huge, mysterious 27% of the universe that is dark matter.
So lensing isn't just one tool. It's like a cosmic Swiss Army knife. We use it to map the invisible scaffolding that holds the universe together. We use it to find new worlds. We even use it to measure how fast the universe is expanding. And by using massive galaxies as natural telescopes, we can see farther back in time than ever before to study the very first galaxies being born. But if you want the single best piece of evidence, the smoking gun that dark matter is real, we have to look at an absolutely epic cosmic car crash called the Bullet Cluster.
What you're seeing here is the aftermath of two huge galaxy clusters that smashed right into each other. Now the normal matter, mostly hot gas, shown here in pink, it slammed together, created a huge shockwave, and got stuck right in the middle. But look at the blue stuff. That's a map of where all the mass is, traced by weak lensing. And most of the mass, well, it didn't even slow down, it just passed right through.
This is it. This is the smoking gun. You have the visible matter in one place and the source of most of the gravity in a completely different place. There's really only one way to explain this. Most of the mass has to be in some kind of invisible substance that doesn't interact with normal matter at all. The dark matter just ghosted right through the collision. Incredible.
Discoveries like the Bullet Cluster have been absolutely foundational, but honestly, we're just getting started. The next few years are shaping up to be a true golden age for the science of gravitational lensing.
I mean, right now, the James Webb Space Telescope and the Euclid mission are already sending back data that is blowing astronomers' minds. In 2025, the Rubin Observatory is going to start a survey of the entire sky that will find thousands upon thousands of new lenses. Then, in 2027, the Roman Space Telescope will launch, and it's projected to find something like 1,400 new exoplanets using microlensing. The pace is just accelerating like crazy.
So gravitational lensing has gone from this quirky, theoretical prediction to one of the most powerful tools we have for understanding the cosmos. It's showing us the universe's hidden secrets, from tiny rogue planets to the vast, invisible web that holds everything together. It really turns out that the universe itself is the best telescope we could have ever asked for. And the biggest question of all is, what is it going to show us next?